We're now ready to begin exploring the translations and transformations of graphs. Now, why are these transformations important? Well, up until now, we've had to create a table of x and y values every time we want to sketch a graph. But when we are able to identify individual translations of a parent function, this makes graphing substantially faster. So the first translation that we are going to be exploring is vertical translations. So to begin, let's suppose that we have the given function y equals f of x. Now, we are going to refer to this function as the parent function, or the basic graph. The effect of adding a constant to or subtracting a constant from this parent function is a shift of the graph of the parent function either up or down, respectively. So let's put this into more formal terminology. So we have that for some positive constant k, we have the following. So we say that the graph of y is equal to f of x plus this constant k is the graph of our parent function, but it's shifted up k units. Now, alternatively, we have the following. So we say that the graph of y is equal to f of x minus this constant k is, again, the graph of our parent function, but this time, because we're subtracting a constant from f of x, the graph is being shifted down k units. So to better help us understand these vertical translations, let's go ahead and consider the following example. To better help us understand these vertical translations, let's go ahead and graph these two functions. And here we are given g of x is equal to the absolute value of x plus 2. And we have h of x is equal to the absolute value of x minus 3. Now, before we even get started here, let's begin by identifying the parent function for both g and h, and then describing the translations of those graphs from the parent function. So to identify a parent function, we can simply take our fingers and cover the constants that are in each of the functions, which allows us to see that our parent function here is y is equal to, we'll say, f of x, or the absolute value of x. So looking at the graph of our parent function, we've labeled a couple of points that we are going to map to these new functions to help us appreciate the vertical translations. So let's begin by considering the function g of x. So we have that g of x is equal to the absolute value of x plus 2. So we are adding a constant 2 to the parent function. So we can say that g of x, so because we're adding that positive constant to the absolute value, we can say that g of x is going to shift the graph of the parent function up 2 units. So if we start here at the vertex of our absolute value, this vertex point is going to be shifted up 2 units. So we have a new vertex at the ordered pair, 0, 2. And the same thing's going to happen with these other points. The ordered pair, -1, 1, is going to be shifted up 2 units to the new ordered pair, -1, +3. And very similarly, we're taking this other point, 1, 1, on the parent function and shifting it up 2 units. So connecting these 3 points with 2 straight lines, we can see the graph of g of x, which is the absolute value of x plus 2. So the shape of the graph has not changed, it's just been translated up 2 units. Now similarly, let's go ahead and consider our second function, h of x. Now here, since we're subtracting a constant 3 from the parent function, this is letting us know that this function shifts the graph of the parent function down 3 units on our y-axis. And again, starting from our parent function, its vertex, we're going to take this point and shift it downwards 1, 2, 3 units. producing the new vertex 0, negative 3. And very similarly, we're going to take these other 2 points from our parent function and shift both of them down 3 units as well. And connecting these transformed points, we can see the shape of the graph for h of x. So again, we can see here that the shape of the parent function's graph hasn't changed. It's just moving up or down along the y-axis.